Our first talk this afternoon will be by David Mateos, who will tell us about QCD.
Thank you. So I hope I convinced you yesterday that by exploiting a universal fact about ADS-CFT, namely the fact that a deconfinement phase in a gauge theory is always related to having a black hole in the background. By using that, you can extract at least some universal predictions within the supergravity regime. In particular, we talked a lot about the calculation of this ratio, which in this particular case happens to be applicable, at least in some regimes, it seems, to QCD. So what I'd like to do today is to put together this fact with another universal fact, or rather universal fact, which is that introducing quarks, typically these theories that you come across in simple examples of ADS-CFT only have adjoint matter. If you add quarks, at least in the limit in which NF is much smaller than NC, that corresponds to having D brane probes in this black hole background. So what I'd like to see today is what can you derive by putting these two things together. Okay. So in this case, we'll be looking at now D7 branes in a background where there is a horizon. There's a black hole in the background. I'm suppressing the directions along the gauge theory. And of course, as soon as you think about it, you realize that because you're adding energy to the original supersymmetric configuration, you're adding energy to the background, proportional or associated to the temperature. That's now going to deform the 7 branes because the gravitational attraction will pull them down. And so remember, we call this coordinate rho, and this one here z. In the supersymmetric case, z is just constant. The branes lie at a constant distance from the D3 branes, if you like. In this case, you have to actually solve for z of rho by minimizing the effective action for the 7 branes in this background, which is the Dirac-Born-Infill action. And we won't do this explicitly because in particular, you can't, in most of the cases, you can't find analytic solutions, but you can do it numerically. And I will be telling you what results you get. But the one thing you know is that asymptotically far away, this falls off as a constant plus another constant divided by rho squared plus subleading terms. And I'd like to spend a couple of minutes explaining the meaning of these constants. This one here corresponds to the non-normalizable mode. Of this field. And remember, it was very intuitive that it is proportional to the quark mass because it's the asymptotic distance in the UV, which is where you specify the Lagrangian of the gauge theory. It's proportional to the coefficient in the gauge theory action. MQ is the coefficient that multiplies the operator psi bar psi, where psi is the fermion in the fundamental representation. And similarly, this one here, this C, is the coefficient of the normalizable term. And as usual in ADS-CFT, the normalizable coefficient corresponds to the vacuum expectation value of the dual operator in whatever state you're looking at. So C is proportional to psi bar psi. So the idea is that you fix the non-normalizable mode at infinity. That means you specify the quark mass, or the coefficient of your operator. You specify the action for your theory. And that should determine, once you integrate the equation of motion and you demand regularity, that should select what the second coefficient is, and therefore determine what the VEF of the corresponding operator. The dynamics determines the VEF of the operator. Any questions about that? No? Okay. So as soon as you draw a picture like this, you immediately realize that at least there are going to be two distinct phases for these D7 brane embeddings. So let me draw a picture over here. The first one, as I drew it over there, looks like this. But of course, remember this asymptotic distance is proportional to the quark mass, and the size of the black hole horizon is proportional to the temperature. So you immediately realize that if you, for example, fix the quark mass and increase the temperature, eventually the gravitational attraction will pull down the branes and they will fall through the horizon when this becomes big enough. Okay? When the temperature is small enough compared to the quark mass, the tension of the branes is still enough to counterbalance this gravitational pull, but eventually, when the horizon becomes big enough, the branes will fall partially through the horizon, not totally because you're fixing the boundary conditions at infinity, but the configuration that will minimize the energy will be of this type. So we will call these ones, because the induced metric on the branes here has no horizon, it's a perfectly smooth horizon-free geometry, we will call these ones Minkowski embeddings, and these ones here black hole embeddings, because the induced metric on the 7 branes clearly now will have a horizon in it. Okay? It happens that, in fact, there is an intermediate solution between these two that looks like this. At which the branes just, so to speak, touch the horizon at a point. And we will call this the critical embedding. And so, given that it looks like you could actually go from one to the other through this one, you may suspect that this phase transition is going to be second order, is going to be continuous. But in fact, that's not true. To decide whether or not that's the case, you have to do the thermodynamics. That means you have to compute the free energy of these different configurations, where you fix for each value of the quark mass and the temperature, you compute the free energy, and you plot that, and you see for these different values which one has the lowest free energy. So let me plot over here what you get. So I'm going to plot F. By the way, F, of course, what you do is you take the D7 brane effective action, you Euclideanize it, and you identify that with beta, which is 1 over the temperature, times the free energy. And you think of this free energy as the free energy of the contribution to the total free energy in the gauge theory coming from the fundamental degrees of freedom. There's a bigger contribution to the free energy, which is fixed here because we're not changing the background, that comes from the glue. And that would be just a supergravity action. But we're just focusing on this term. So if you plot that in units of lambda, nf, nc, t to the 4th, as a function of t over m gap, and remember that m gap is equal to, or goes like mq over root lambda, you get for the Minkowski phase. So what I'm doing is I'm fixing the quark mass, or if you like, I'm plotting just a dimensionless ratio of T temperature over the quark mass divided by lambda. you get that the Minkowski phase has a free energy like this, and the black hole phase has a free energy like that. And you see that they cross at a point, at a value where this ratio is of order 1. And what this means is that when T over this mass scale is on this side, then the Minkowski embedding is preferred. Whereas when you cross this point, it's a black hole. This is the black hole branch, and this is the Minkowski branch. The black hole branch is preferred. And in fact, Minkowski embeddings only exist down to a minimum value, sorry, to a maximum temperature. If you go above that temperature, they just don't exist. But even where they exist, they cease being thermodynamically preferred when you reach this point, and vice versa if you come from the other side. Is that clear? Yes, Harvey. Sorry?
What happens to the black hole curve if you move to the right?
This one here? It also ceases to exist because if you go to temperatures that are very low, then the black hole is very small and there's just no black hole embedding. Oh, if I move here? If I follow this way?
No, the other one.
This one?
Start on it and just follow it round. Yeah, that's right. What happens if you extend that in?
Oh, what I'm giving you here, okay. I'm giving you a zoom into the region where the phase transition takes place. I can show you the entire plot if you like. Maybe I could even show you that later. Unless you really want me to draw it right now. Okay. Good. So if you plot, for example, once you have the free energy, you can compute the entropy density. Which is just minus df dt. And that looks something like this. So this point here and this point here, A and B, are the points between which the transition takes place, because this is just the derivative of the free energy, and you see that the slope is different, so there's a finite discontinuity in the entropy density. And the same is true for other thermodynamic quantities like the energy density, etc. Is that clear? Good. So what that means is that the transition is actually first order. It's a first order phase transition. For example, the chiral condensate also jumps discontinuously across the phase transition. And what I'm going to do in the next little while is to discuss the physical aspects of this phase transition, what it means, and some of its interesting properties. So first of all, you note that the entropy density, the free energy, in particular, let's say the entropy density, but the same is true for other thermodynamic quantities, goes like lambda nf nc t cubed. Now, this factor here, this dependence on nf and c, that's expected because this is the number of degrees of freedom in the fundamental representation. So remember, this free energy or this entropy density is the contribution to the total free energy or entropy density coming from the D7 branes, which are dual to the fundamental degrees of freedom. There's an order nc squared contribution from the glue, which would come from the supergravity part of the action in the gravity description. But you also note that, of course, this factor, you could have gotten it by large n counting. You expect that. But you see there's an enhancement there's a power of lambda here, the tooth coupling, at strong coupling. So let me tell you where this power comes from, or at least let me interpret it a little bit. On the gravity side, so you know, I just told you that the total entropy will be some number times nc squared times t cubed plus, so let me factor it out, times 1 plus another number, which you could read off from there, times lambda nf over nc plus etc. So this is the contribution we've computed. So you see, it's suppressed with respect to the glue contribution by lambda nf over nc. Now, this coefficient here is just Newton's constant times the tension of the D7 branes. This goes precisely like lambda nf over nc. Okay, because g Newton goes like gs squared. The tension goes like nf over gs. So you get gs nf, and gs is g squared Young-Mills, which is lambda over nc. So this also answers a question that I got the first day, I think, about what is the scale, or what is the parameter that controls the back reaction of the 7 branes. You could have imagined, or you could have thought, that it's nf over nc. It's actually lambda nf over nc. Okay? That's the explanation of that factor from the gravity side. Now, from the gauge theory point of view, this factor can be understood, at least to a certain, with a caveat that I'll mention. If you rewrite it, lambda nf nc, that is g squared Young-Mills nc times nc, that's nc squared, so you get nf nc squared. And this is precisely the way this diagram scales. This is a diagram, this is a loop correction, a quark loop correction to the, say, the free energy or the energy density in the vacuum coming from the gluons. Okay, if I remove this, what I have is just a closed loop of glue, and that's the leading contribution to the vacuum energy density coming from the plasma. And when you incorporate this first correction coming from the quarks, that scales in this way. But before I take that question, let me caution you that this is a perturbative argument. Okay, this is a Feynman diagram. This result here is valid in the opposite limit, at lambda going to infinity. And so, even though it's suggestive, you should take it with caution. Mukul.
I'm just going to go back to your gravity scaling as
Yeah.
lambda nf over nc is the back reaction.
Yes.
If lambda is large for any small value, even for nf equals 1, this is a large back reaction, isn't it? Are you imagining scaling nc to infinity before scaling lambda up to infinity?
What I'm imagining is that the way to think about the large n limit is not that you send nc to infinity. This is my point of view. It's an expansion in powers of 1 over nc, or 1 over nc squared, nf over nc, and 1 over lambda, for large lambda. And so, in order to guarantee that the calculation I'm doing makes sense, because I'm treating the D7 branes as a perturbation, I have to be in a regime where lambda nf over nc is small, not just nf over nc. And of course, you can achieve that in different ways. Any more questions? Okay, so let's now ask, what is the main difference physically between these two phases? Okay, we just saw that actually this one is skipped over by the phase transition. I'll come back to this one later, but for the moment, it's not thermodynamically, it's actually unstable. So, well, one of the main differences is in the spectrum of mesons. And that's something you can already conclude without actually doing any calculations from what I said the first day, but let's go over that. So what does the spectrum look like in the Minkowski phase? Well, because the induced metric on the 7 branes has no horizon, you see it closes off smoothly, It's just a slightly more complicated metric than the one we got the first day. Remember when I drew that cigar? But still, topologically, has the same topology. So the spectrum of mesons is discrete. And it has a mass gap that's parametrically of the same order as at 0 temperature. In other words, it goes like mq over root lambda. But it also has quarks, because I can take a fundamental string, attach it to the 7 branes, and let it fall through the horizon. Okay? That has the quantum numbers of a quark. So here we have finite energy quarks with a mass of order mq. It's not exactly mq because mq is the distance asymptotically between, is the asymptotic value, if you like, of z when rho goes to infinity. But of course, as you move in and you reach this point, that mass decreases. So you should think of that distance as a function of rho as the running mass of the quark as a function of the RG scale. Okay? And this one here, in the far infrared, this is as low as you can get on the 7 branes, or as close as to the horizon as you can get. That's what you would call the constituent quark mass. Okay, that's the mass that will enter, for example, if you form, well, we'll see what it enters. But that's the physical mass that takes into account both quantum and thermal corrections. But it's still parametrically of the same order as MQ. So what you see is that there's a hierarchy between these two sets of excitations, because these ones here, of course, much lighter at strong coupling than these ones. Nevertheless, both of them in the large N, large coupling approximation are absolutely stable. What I mean by this is that the decay width is 0. Okay? In real QCD, hardly any excitation is absolutely stable. It's only in the large N that they become absolutely stable, like mesons and baryons. And here, these quarks are also absolutely stable. Yes?
All holographic versions of QCD have these free quarks that are large.
Say that again?
All holographic versions of QCD have some large mass. The Sakai-Sugimoto model also has this.
Yeah.
It's really very different. It's not really confining. It's just down.
I'll get to that. But yeah, it's rather generic, and we'll also get back to that. Any more questions about that phase? Okay, now what is the spectrum like in the black hole phase? Well, in this phase, as I'm going to elaborate over and over again today, there are actually no quasi-particle-like excitations. Okay? There are no narrow resonances that you can identify as particles. At most, what you have are collective excitations. This is one of the main messages I want to convey today. One of the main messages is that in a phase like this, okay, any perturbative intuition that you may have, because that's based on quasi-particle, on the quasi-particle concept, you have gluons and quarks, etc., is most likely incorrect. And so one of the things that part of the power that ADS-CFT has is that even though its precise quantitative predictions for certain observables may be wrong or may not be applicable to QCD, it gives you a completely different intuition to think about strong coupling. And we'll see that in the rest of the lecture. That's one of the main messages. Okay, so qualitatively, it's a completely new tool that in many occasions it's much more appropriate than anything you can do with perturbation theory. So, as I said, in this case, there are no quasi-particles, at most only collective modes. For example, hydrodynamic modes, as you've heard a lot about today. Now, one of the things that I also want to emphasize is that this first order phase transition is not, strictly speaking, a deconfinement transition. Okay? The theory is in a deconfined phase both here and here, because remember I said that whenever you have a black hole in the background, you're in a deconfined phase. So what that means is that if you compute a Wilson loop, for example, both here and here, you will not get an area law. The quark-antiquark potential at very long distances is not linear. Okay? Nevertheless, there is a first-order phase transition that is characterized by the change in the behavior of the physics of the fundamental matter of the quarks. Now, this phase transition occurs separately from a deconfinement phase transition, provided the transition temperature at which it happens, which we'll call T-fun for fundamental, and which you see from here that is of order m gap, because remember I told you the transition takes place at T over m gap of order 1. So this is of order m gap, which is of order mq over root lambda. So this is a separate phase transition provided this temperature is higher than the deconfinement temperature. So the idea is that so even though I'm discussing this in the context of n equals 4 with fundamental matter, you could do it in a theory that confines at low temperatures. Okay, so then if the quarks are sufficiently massive, you will have two phase transitions. You will have one where you start with your D7 branes in a background that has no black hole in it. As you heard this morning, if you don't have a black hole, that's typically a confining phase. So this will be the confined phase. At some temperature T deconfinement, you will jump to a situation in which you nucleate the background that dominates, the geometry that dominates the path integral is now a black hole geometry. Okay? But if the quarks are sufficiently massive, when that happens, the branes will just be pulled down a little bit, but they will not fall through the horizon. And then as you keep increasing the temperature up to T-fun, they will eventually fall through the horizon. Okay? This is a situation where this temperature is larger than this one. If this one is smaller, what happens is that as soon as you nucleate the black hole, the branes want to fall through the horizon. And then there is only just one phase transition at which you both deconfine and melt the mesons. By the way, this phase transition is sometimes referred to as a melting of the mesons or ionization of the mesons because you break them apart. Even though I think ionization is not the process that actually takes place, but we'll have a little bit more to say about that. But we'll just call it melting or something like that. Any questions about this part? Okay, so you could ask, what is keeping the mesons bound in this phase, given that I just told you that there is no confinement in this phase? So let's clarify that. What's happening is that the statement about confinement is an infrared statement. It's a statement about what happens to a quark and an antiquark at asymptotically large distances. Okay? So in a confining theory, if you plot the quark-antiquark potential as a function of the...
I mean,
yes.
the point, the issue with the difference between one that's confined and the black hole, I mean, there's a horizon that's formed. You can have horizon without having a black hole, ADS, for example.
I
Again,
mean,
that's not confined.
I mean a finite temperature horizon, or a finite entropy horizon.
Okay.
Okay, so if you plot the quark-antiquark potential in a confining phase, you will get a linear potential all the way out to infinite distance. You don't agree?
Not if you have dynamical quarks.
I said in a confining phase. QCD with dynamical quarks is not a confining theory.
No, I disagree. Confinement you can state is that there's only color singlet excitation.
Okay, you can define it in more than one way.
There's no order parameter in that case.
Right. Let's, for the purpose of this discussion, let's just talk about the Wilson loop at asymptotically large distances. So in that case, for infinitely heavy quarks, you get a linear potential. And what's happening here is that you lose this property for large distances, because if you hang a string, so I should probably draw another picture. Let me draw it over here. So this is another picture in which I'm focusing on the gauge theory directions, x here, and this is the radial direction. This is the bit that's filled up by the 7 branes, but they don't come all the way down to the horizon. So this is the boundary, and this would be the minimum distance reached by the 7 branes. So if you look at a Wilson loop for a quark and an antiquark, for short distances you still get a linear potential, essentially because this string, when it's very short, doesn't know that it lives in ADS. It doesn't. The scale is much shorter than the ADS radius. Okay, so you get the same result as in flat space. If you pull apart a quark and antiquark with a string stretched between them, you get a linear potential. But then, when the string becomes very long, eventually it can break because it can fall through the horizon, and that's what tells you that there is no confinement. So over here, this flattens out. So this would be the confining case, and this would be the case at hand. There is another way in which you can explore and actually convince yourself that this is the case, which is by, instead of looking at the Wilson loop, you can look at rotating mesons that have some spin, J. And for J not too large, but large enough so that you can treat the string as a classical string, you get a Regge trajectory, which signals the fact that you have a linear potential. Whereas that gets modified for sufficiently long strings, and eventually they break. So to summarize, the fact that you don't have confinement doesn't mean that you can have something that looks confining at sufficiently short distances, and then you can have bound states if this well here is deep enough, or if this distance is long enough. And in fact, if you do the calculation, you realize that this scale at which this significantly deviates from a confining potential is given by m gap inverse. So it's perfectly consistent. What I'm saying is the typical size of these mesons is set by their inverse mass. And that's the scale at which this effective potential is still confining. So these mesons are bound by an effectively confining potential, even though, strictly speaking, in a technical sense, the theory is deconfined. Is that point clear? You asked a lot of questions yesterday, and I'm not getting any questions today. Is it because I'm going too fast, or I was going too slow yesterday? Or? Yes?
I actually do have a question then. seem to remember from Larry Effie's lectures last week that he said that if you have a certain separation with the quarks, the more appropriate picture is not a string stretching between the quarks, but just two strings stretching straight down, interacting by graviton modes or something.
No, that depends on the distance between them.
Yeah, he said from a certain distance on. So
From a certain distance on, yeah.
is that the same case for your discussion? Or?
Yes, so if you pull them apart too far,
Yeah.
then it's energetically preferred not to have something like this, but to have something like that.
But how do you decide then that, I mean, if you pull them apart too far, either the string falls through the black hole and you say you have a non-confining theory, or you say you have two straight strings interacting by graviton modes, which might again be confining.
No. So what you have to do is to decide what configuration is the minimum energy configuration.
Right.
If the quark and the antiquark are very close together, clearly this configuration has a lower energy because the string is shorter than these ones. Once the string breaks, okay, naively you would say there is no force anymore because now I have two independent pieces of string that I can pull apart. But that's not strictly true because they can still interact by exchange of gravitons and other supergravity fields.
Yes.
But that's not going to change this curve into something that's still confining. It will modify the effective potential, but it will not give you confinement.
So in the confining case, the string basically never breaks then.
That's right. And that's because in the confining case, instead of a horizon down here that the string can go through, what you get is that your geometry just closes off smoothly. There's a bottom to your geometry. And then, if that's the case, the string cannot just end anywhere. It has to always stay connected because the endpoints, either they go through a horizon or they are attached to the 7 branes. And so in that case, what happens is that the minimum energy configuration for large separations is something that looks like this. And so you see that the main contribution to the energy for long distances, these pieces give you a subleading contribution, and you get something that's linear in the distance because it's just the energy of this bit down here. And that's where you get a linear confining potential.
Don't you still get a potential of this shape because at some point what happens in QCD happens, which is that the string breaks by quark-antiquark pair production and you end up with
Yeah, but that's
so it still levels off.
but that's subleading in the large n expansion.
Oh.
At large n, that is a subleading process. The quarks just are subleading in the large n.
But you could see that here, right? You could see it in the picture.
How, if you have a confining geometry, how is the string going to break? Oh, you want? Oh, sorry.
It breaks
I'm
by
sorry. Yes.
realizing
You
can
want to
fluctuate all the way up in the middle and come down.
Yes, but that's suppressed. That process is suppressed.
I see.
And you can also understand that because it requires a large fluctuation from here to go to here. Yes, Mugen.
I just wanted to clarify a bit about this picture of
About what?
about the confining potential near the origin.
Yes.
So is this do you think this is whether this is a feature of the leftover confinement above the deconfinement transition, or is it something just about a feature of quarks moving in some medium? If I have to understand this potential microscopically, see what I
It's
mean?
not. It's right. It's not a property of the medium because this is still true at 0 temperature. Yes.
I think it's a feature of confinement in this theory.
Not even so. Not even so because, first of all, this is not a confining theory. This is n equals 4 with quarks. So, and at 0 temperature, it's just not a confining theory. Nevertheless, so if you like, it's a theory that at 0 temperature gets it completely wrong. Because at 0 temperature, what you get is a linear potential at short distances, which is not what you get in QCD, okay? And at long distances, you get a Coulomb potential, because the string then feels that it's in ABS, which is not what you get in QCD. But in this case, and thinking of this as a model, then, as I'm going to say now, it's in good agreement, at least semi-quantitatively or semi-qualitatively, with some results from the lattice. So let me move to that then, unless there are other questions. Yes.
Yeah, yes, one question. Actually, I asked it to David Kudasov to talk as well. But Perhaps that's a good point. Yeah, the thing is that you have a hierarchy between the quarks and the mesons. The mesons being the point is that if you're at sufficiently low energy, you wouldn't be able to tell the difference between. You wouldn't be able to know whether it's confined or not until you got up to that energy scale. Now, obviously,
Not really, because if I go up to a scale of order m gap, mq over root lambda, meaning, for example, I heat up the system up to a temperature of this scale, which is much, it's at the bottom of the hierarchy. I will undergo this phase transition, and once I'm here, I do see immediately, even in the lightest excitations, that I'm in a deconfined medium.
okay.
And also,
how big is? Can you tune the gap? I mean, maybe you can't reach this temperature.
let me add something more. I'm focusing here on the dynamics of the mesons, but of course, even in this phase, you have a black hole in the background. So, for example, you don't have a discrete spectrum of gluons. You have a continuum. So these two phases are distinguished by the behavior of the mesons, but as far as the glue is concerned, you still have a medium where you're in an absolutely deconfined phase. Does that answer your question?
Yeah, although, well, no, partly, but I mean, the question was really about why do we know that QCD is right? Because how do we know that at some high energy scale, this phenomenon won't, quarks won't suddenly be defined? They exist, but we haven't been able to find them yet because we haven't reached the appropriate energies.
Well, I would say that.
I mean, okay,
if I were an experimentalist, I would tell you you don't know.
That's the question that I was asking David Kudasov, because he pointed out a similar phenomenon. I mean, it seems to be a rather phenomenon that comes up in a lot of different approaches. I think David Groth convinced me that I couldn't be right in the real world.
Well, if David did that, no. Okay.
It's nice to get a second opinion.
Well, that's very flattering. Did you have a question? Are there any? Oh, sorry. Yeah.
I'm just a bit confused about the mass gap being inversely proportional to the coupling constant. I mean, shouldn't you formally take that to be, take the coupling to infinite and you don't get a gap at all? And if you don't, then shouldn't you include corrections in other places?
I'm not sure I understood the logic of your statement. What's the apparent?
This results for the mass gap.
Yes.
It was deduced from the supergravity side, right?
Yes.
There you should take the hand-tooth coupling to infinity.
Yeah, this is only valid for large tooth coupling, yes.
Okay,
that's why
not
there's
infinite.
a hierarchy.
Okay, but not infinite. Yeah.
Not infinite.
Then shouldn't you include corrections in other places?
No, this is the leading order result at strong coupling. This, even the mass gap, will receive corrections that perhaps will go like 1 over lambda to the 3/2 or something like that. So this is just saying at very strong coupling, the mass at leading order is given by this. But this will receive, of course, corrections when you expand away from lambda equals infinity. That will be subleading with respect to this result.
But you are already,
As I said,
already taking it to be just large, not infinite.
yes.
It should be 0 then. Shouldn't you include corrections in other places?
No, this is an expansion in, if you like, in 1 over root lambda. So m gap is going to be mq over root lambda times 1 plus order 1 over root lambda. So there are corrections to this result.
Sure.
This is like saying, let me see if I can give you an example. For example, the eta prime, the mass of the eta prime at large n goes like 1 over n. Of course, that at finite n has corrections. It's going to be 1 over n times 1 plus something that scales like 1 over n. So this is just the leading result. Does that answer your question? Or?
I'm not entirely sure.
This is like, you could have asked me, for example, the ADS radius goes like GS, NC, so it actually goes like lambda and s to the 4th. So you could say at strong coupling, or if you take the strict limit, this is infinite.
But the meaningful thing to compare there is the quotient of the radius reduced to the string length.
Yeah, but that's lambda.
It's still lambda.
Yes. But of course, this is I insist again, this is an expansion, and we're not setting anything to infinity, it's just an expansion. Any other questions? Okay, so as I was saying, the result that sufficiently heavy quark-antiquark bound states survive as bound states above the deconfinement phase transition is in good qualitative, it's actually in good qualitative agreement with the lattice and in reasonably good quantitative agreement. So let me discuss that. People who do lattice simulations and compute spectral functions see peaks in those spectral functions that they interpret as narrow resonances corresponding to mesons that have survived deconfinement. Okay? So for example, if you look at the Jape psi, which is a bound state of a charm and an anti-charm, and which has a mass of order 3096 MeVs, depending on what lattice simulation you look at, they tell you that this seems to survive at up to the highest estimate is that the temperature at which it melts is around 2.1 T deconfinement. Now, T deconfinement is something that is also calculated on the lattice, and depending on what result you look at, goes between 151 and 192 MeVs. So if you plug it in here, this tells you that this meson survives up to temperatures of order between 317 and 403 MeVs, which is above the deconfinement temperature, of course. If you now estimate what this temperature is from the gravity description, all you need to know is that I told you this temperature is of order m gap, namely it's of order the mass of the meson at 0 temperature. Okay? So all I need to tell you is the proportionality coefficient here, which is something you can read off from our paper, and that turns out to be 0.12 times m meson. So this is 0.12 times 3096, which gives you 371 MeVs. And you will notice that this is exactly the same as the lower bound if you exchange the 7 and the 1. So hopefully that's a convincing argument that you're doing something right. Now, of course, you shouldn't take the number seriously. What you should take seriously is the statement, the qualitative statement, that for sufficiently heavy quarks, the corresponding bound states survive the confinement. Because that is true not only for the D3, D7 system, but for any system consisting of a black hole in the background together with D-brane probes that model fundamental matter for you that I know of. And the reason it's so universal is, again, because it only depends on the fact that deconfinement means that you have a black hole in the background, and the fact that for a small number of flavors, you can represent them by D-brane probes. Okay? So that is another universal statement that follows, at least within the supergravity approximation, that's completely model independent. David?
What strikes me as more surprising is not that individual bound states survive, but that Reggie trajectories survive. Because that's really suggesting the confining string is still somewhere around. So is there any hint of that from the lattice?
They only survive up to a given angular momentum.
I understand, but,
okay.
but even that they survive at all is what strikes me as, you know, Reggie trajectories is what we all learned was the hint of confinement and therefore of strings. And here we're seeing them in a place where there is no confinement. So is there any hint
in a way, what I'm
they survive?
Sorry, is there any hint where?
In QCD, can you start plotting?
Oh, in QCD.
Daughters of the Jape psi.
Oh, good point. I don't know actually. You would have to. what you're asking is, if I look at excited states, say of the Jape psi, in the deconfined phase, do they lie on a line? Okay, I don't know the answer to that. I suspect nobody knows the answer to that because calculating, you have to calculate spectral functions on the lattice in the deconfined phase and then look at, well, first of all, you calculate them in the Euclidean formulation. Then even extrapolating that to the Lorentzian, continuing that to the Lorentzian signature, is not something you can do straightforwardly. So you have to put in some assumptions about the form of the spectral function that you expect. If you could calculate the correlator in Euclidean signature exactly, you could then perform the inverse transform and get the analytic form of the Lorentzian correlator. But if you make a small error bar in the Euclidean one, you can see that can translate into a huge difference in the Lorentzian correlator, which is what you need to identify these peaks. Okay, so that's a very non-trivial thing to do, and people have done it for the lowest states, maybe one or two. In fact, I think they've looked at the first excited state. But I don't think you have enough to put them on a graph and see if you get a linear trajectory. Yeah. Okay, so any more questions about that? Good. So I've been telling you about the mass gap and so on in this phase. Let me be a bit more precise about what that means. Remember that here we are working at finite temperature, and finite temperature breaks Lorentz invariance. Okay? It breaks boost invariance. And so what do I mean really by the mass of a particle? What you should be really looking at is at the dispersion relation. So each mode will be characterized by some energy, let's call it omega, and some free momentum k. And of course, in a relativistic theory, you know that omega squared minus k squared is equal to the mass squared. But that's no longer true here because Lorentz invariance is broken. And so the dispersion relation is the relation that tells you what the energy is as a function of the free momentum. Again, in a relativistic theory, this is just square root of k squared plus m squared. But you don't know a priori what that is here. And this is going to tell you how any excitation, in fact, propagates through the medium. Once you specify the free momentum, that's going to tell you how the energy depends on that free momentum. So let me tell you what you get, because this is also very generic. And I think the consequences of this have not completely been appreciated. So if you plot omega as a function of k, the modulus of k, the statement that there is a mass gap in the spectrum means that at zero momentum, so for a particle at rest, the energy has some finite value above 0, finite and non-zero. But then, for very large k, so this is something you know from the arguments I've given you. Now, for very large k, what you find is that this approaches a line. So omega goes like, actually is equal to, for asymptotically large k, v, some velocity times k, where v is smaller than 1. And so what this curve does is something like this. So here, let me plot the light cone. This is the line omega equals k. Now, why is it generic that this moves at a subliminal speed at very large k? The reason for that is that for very large free momentum, the wave function of the meson, remember mesons are fluctuations of the D7 branes, okay? Now, those fluctuations have some radial profile. But for very large momentum, that radial profile localizes more and more near the tip of the brain, because the energy of the mode is bigger and bigger, and gravity pulls it down. So it localizes at the tip of the brain. Okay? It's moving, so the gauge theory directions here would be coming out of the board, and it's localized down here. And of course, there's a redshift for the propagation for the local speed of light here. That's what's giving you the fact that v is smaller than 1. So this is, again, a generic consequence of this setup. And the reason I'm emphasizing this is because I want you to note, first of all, that this becomes space-like. The momentum, the form momentum of these mesons in this region is space-like. What I mean is omega squared minus k squared is negative. Is that clear? Yeah, that's correct. Okay? And again, I also want to emphasize that it crosses the light cone. What this means is that each of these modes, generically, if you give it an appropriate free momentum, it will have, for some value of the free momentum, omega will be equal to k. So the excitations in this plasma, for each of these mesons, there's a mode that's not at rest, but that has a null momentum. Is this clear? I think this could give rise to Cherenkov radiation in this type of medium, but that's something that we're working on, so I don't have anything very deep to say about that, but I think it is relevant. And the reason I'm emphasizing it is also because the existence of this point is going to be important when I calculate a spectral function for electromagnetic currents, because those currents couple to a photon, which is massless, and the only way it can couple directly to one of these mesons is if you have a meson with null momentum.
This is we're talking about dispersion relation for these mesons.
Yes.
So they become tachyonic. Especially high.
No.
Well, by definition, it's a tachyon.
Well, by definition, you can call it a tachyon, but
I mean, it's not
they
what
move.
people often mean by tachyon.
It's just an excitation that moves at a speed that's smaller than the speed of light. So what I mean,
Tachyon, yeah.
no, what I mean, no. What I mean by that is that d omega dk is v is smaller than 1. So there's nothing wrong with these excitations.
Oh, I see. Of course, no. It's the group
The
velocity.
phase
The group
or the
velocity
group
is still-
velocity
yeah, the
is
group
smaller
velocity-
than 1.
The group velocity is still.
So this has nothing to do with any type of instability or anything
Yeah,
like
right.
that.
I don't suppose you know a way to get a dispersion relation that isn't monotonic.
Say that again?
I don't suppose you know a way to get a dispersion relation that isn't monotonic.
That isn't monotonic. No, I don't. I don't even know if that's physically allowed. I mean, there could be some physical principle that
Happens at helium.
in.
Helium.
Really? Maybe you can tell me about that.
Second sound.
Yeah.
Oh, I see.
It's the rotor.
I see. I don't see a way to get that here, but I'd like to hear more about that. Okay, let me then say a couple of questions about stability. Sorry, a couple of things about stability. I told you that if you look at thermodynamically preferred embeddings, you jump from this one to this one. Okay? So you could ask what happens if you look at embeddings of this type that are closer and closer to this one, and the same thing on this side. Okay? So what happens is that when you're sufficiently far away, they are just stable. They are the global minimum of the free energy. Then, for a little while, they become metastable, which means that they are locally thermodynamically stable. They have positive specific heat, for example, but they're not the global minimum of the free energy. But if you supercool the system, for example, or superheat it this way, you could in principle access those embeddings. So these are metastable. And then if you go beyond that point, they become both thermodynamically unstable, and that you see because if you compute the specific heat, that becomes negative. So here they are unstable. So the specific heat is negative. And exactly at the same point where the specific heat becomes negative, the lightest meson goes tachyonic. So m squared becomes negative. Okay? So the thermodynamic instability exactly matches the dynamic instability. So m squared for one of the mesons also becomes negative. And the same, a very similar thing happens if you approach this embedding from the other side. There's a region of stability, metastability, and instability. And the reason I'm saying this is because when we calculate this 2-point function of electromagnetic currents, I will calculate it not only in the stable phase, but in the metastable and unstable phases, because I want to illustrate how, in this phase, when it's stable, there are no quasi-particle excitations. But as you approach this one, quasi-particle and narrow resonances develop, as you would expect, because you know they exist on this side. So in some sense, this is I think, a really nice result, because this is a system where even though you're pushing it into an unstable region, if you forget about that for a second and you compute the spectral function, you see the development of narrower and narrower resonances, implying the appearance of more and more well-defined quasi-particle excitations, as you have over here. Here, your quasi-particles are real particles. They don't decay.
First order phase transition. So would you expect to see any resemblance on either side?
It's first order thermodynamically because you know it jumps, but I can go in off shell if you like.
Or it's what you said,
Thermodynamically
it's a
speaking,
smooth
I can actually go through this embedding. And there are more complicated setups, for example, when you introduce a chemical potential, where in fact you can approach this type of embedding by going along stable configurations. But I'm not doing that just because it's more complicated. I'm going to do it in this model, which is a little simpler, but the conclusion will be the same. Yes?
When you plotted the free energy before, there was like one of these lines in Minkowski embedding, for example, did something like this and came back. There were like for each temperature a couple of Minkowski phases.
Yes.
What does it correspond to?
Good. So that's something that I wasn't planning to discuss. Okay. The reason I wasn't, so let me say it anyway. I've hidden a lot of structure that occurs near this embedding. To give you just the words, what happens is that as you approach this embedding, there's a self-similarity in the system that develops. So when you approach criticality, so forget about stability, okay? Let's just look for embeddings. You realize that the system becomes self-similar. And if you plot, for example, any thermodynamic quantity, what happens, so imagine I plot, for example, the entropy density. So I told you that it does something like this. Yes? But if you focus on this region and you zoom in, what you see is that this is actually doing the following thing. It's spiraling around. And the same over here. An infinite number of times. There's a discrete self-similarity in the system that you can actually prove analytically. And in fact, one of the first, as far as I know, the first person who started looking at the embeddings of brains in a black hole background, in an asymptotically flat black hole background, was Valery Frolov. And his motivation was that he wanted to simulate, in a toy model, Choptic scaling. Choptic scaling is what happens when you collapse a shell of matter, say. If you do the numerical calculations, you discover that the system, near criticality, develops a self-similar behavior, okay? And that's associated to nucleating a black hole. Here, you're not nucleating a black hole because the black hole is there already, but from the point of view of an observer on the brain, you are nucleating a black hole because as you change some external parameter, namely the quark mass, you go from an induced metric that has no horizon to one that has a horizon, and you go through a critical embedding. So it's not surprising that this system also exhibits this discrete self-similarity. So what I did when I plotted this was to suppress all of this for you, because the phase transition, if you look at stability, happens from here to here. And so all this region is in the thermodynamically disfavored region, and so it's not very physically relevant, unfortunately. Because if it had been, then you can compute critical exponents exactly here. And that would have been a precious thing to do, because you might have been able to try to compare with the gauge theory. But unfortunately, I don't really know whether this is very physically relevant. So, does that answer your question? Any more questions?
I have a
Yes.
dumb question. All of these disfavored ones have much larger entropy, so they're disfavored free energy. But there's an infinite number of them. So can you play some game where you just beat that suppression with
No, because
coefficient?
I don't think so. Because the entropy, first of all, the entropy doesn't really change much, because once it spirals in, it's actually, there's a logarithmic self-similarity. So I've blown up exponentially this region for you. You wouldn't see it, right? So it's not really that much different. And in any case, the free energy already is the energy minus Ts. So the entropy is already taken into account. Oh, but you're saying there are a lot of them. Okay.
Yeah, exactly. Yes, you have an exponent which suppresses it, but you have a coefficient
Good.
up front which is exponentially large.
Good. I haven't thought about that. I don't think they are going to be very physically relevant, but I haven't thought about that possibility. Yeah. I think if anything, these ones here that are metastable, those could be relevant. As I learned recently, there's something called spinodal instabilities in phase transitions. And somebody in Berkeley was telling me that he thinks this could be relevant for the hydrogenization process in Greek or LHC. Because when the plasma ball cools down, you're going from here to here, and so there is a phase transition. But sometimes dynamically, you don't go along the thermodynamically preferred embedding. You follow some other path. And you can actually fall into this, and that has some consequences on fragmentation. But anyway, any more questions about this? So I was actually planning to talk today about this calculation of the spectral function, but I don't have time. So what I'm going to do is to close with making a connection to what Shiraz was, or Professor Mingwala was talking about this morning, namely these plasma balls. So he told you that whenever you have a first order phase transition, in his case it was a confinement-deconfinement phase transition, you can have localized black holes. Okay, these are regions where the theory is in a deconfined phase, and outside you have a confined phase. The same is true here, because it's also a first order phase transition. And so there are going to be plasma balls, which are distinguished by the fact that everywhere the glue is in a deconfined phase, but in some region the mesons are in this phase, and in some other region the mesons are in this phase. So let me draw a picture of what that looks like. See if I can get it right. So here's the seven brane. Here's the black hole. But now I'm drawing this direction here is one of the directions I was suppressing, which is the x direction along the gauge theory. Okay? And this one here, so let me draw the black hole. Now the black hole, of course, has a linear direction along the gauge theory. So it looks like this. And these plasma balls are regions on the seven brane that have actually fallen through the horizon. So before, what we had is that either the entire seven brane was outside the horizon, or the whole thing had fallen through the horizon. But these now are localized regions on the seven brane that have fallen through the horizon. So from the point of view of the gauge theory, they look like inhomogeneous in space. And in some region, you have this phase, and everywhere else, you have this one here. So the analogy would be this is the deconfined phase. Sorry, this is the confined phase, and this is the deconfined phase for the mesons. Is that clear? And the stability of these plasma balls follows exactly from the same arguments. If you replace wherever he put nc squared, you replace that by nf and c, everything is exactly the same.
Does that mean that at some point in space you have a critical situation just next to where it goes through the triangle?
Not necessarily, I don't think. Oh, I see. Good point. I haven't thought about that. Yeah, maybe that's true. Yeah, I would have to think about it. So I don't think it's worth that I start with talking about photon production, which is what I wanted to do. So are there any more questions? We have, I think, 2 or 3 minutes, or 5. Harvey?
How explicitly are these linear solutions now?
They're not known at all. I am conjecturing they exist after Professor Mingualo. So yeah, they're not known. The explicit solutions are not known.
With the domain wall, you could maybe just try and solve.
Yes, exactly.
separating vectors,
Exactly.
right?
That would be the simplest one. Yes. Yeah. Any other questions? Okay. I guess we can leave it here then.
Okay, let's thank David for